welcome to the Thermo channel. You may have had this situation. Your friends or relatives are coming to your home and you do not have any sodas or drinks that are cold ready to serve. And you may have heard that if you take ice water and you throw in salt, the temperature will drop and then you can cool your drinks faster. So this is what this video is about. First, let's take a look at what we will need. Of course, we need water, and I have here in a nice bucket, I have about 1 kilogram of water. It's about 7 or 8 degrees at this point. I have ice cubes, and what I'll do with the ice cubes is to put them into the water to bring it next to 0 degrees Celsius, as close as possible to 0. And then I'll remove the ice cubes, and then I'll put about 200 grams of salt. And we'll keep track of what happens to the temperature as the salt dissolves into the water. By now I have already added the ice to the ice bucket, and I'm waiting for the temperature to drop as close as possible to 0 degrees Celsius. The temperature has dropped to between 0.5 and 1.5 degrees Celsius by now. And what I'll do, I'll remove the remaining ice cubes and then add sodium chloride.
The initial temperature is very close to 0, and now we add salt and speed up the movie. The final temperature of the experiment is about -1 degree Celsius. Despite the below 0 temperature, the solution remains in the liquid phase and there is no indication whatsoever that freezing takes place.
Let's now use some literature data on the heat capacity of pure water, pure sodium chloride, the solution, and the heat of mixing, and make some calculations about what happened during this experiment.
To calculate the effect of dissolving sodium chloride in water, let's solve the following problem. 0.2 kilograms of sodium chloride at 25 degrees Celsius and 1 kilogram of liquid water at 0 degrees Celsius are mixed adiabatically at atmospheric pressure. Find the temperature of the solution formed in this process. And this process is very similar to the process that we carried out in the video. The data available are the specific heat capacities of water, sodium chloride, and the solution, and the enthalpy of dissolution of sodium chloride in water at 25 degrees Celsius. This image illustrates the process. The initial temperatures of sodium chloride and water are known, and the unknown is the final temperature of the solution. Here we start with a fairly general form of the energy balance, and we will cross out the terms that are not applicable to this problem. There are no input streams and no output streams, and therefore the enthalpic terms that are associated with streams are cancelled. The process is adiabatic, and therefore the heat transfer rate is crossed out. There is no shaft power in this process, and we cross out the corresponding term. The changes to kinetic and potential energies are also irrelevant in this problem. Equation 2 shows the remaining terms after all these cancellations. We now transfer the PDV term to the left-hand side of the equation, as shown in equation 3. We now remember that the process happens at constant pressure. Therefore, the pressure can be placed inside the differential without changing the equation. The fact that the mass also remains constant allows us to write equation 5, in which we took the mass outside the derivatives and used its specific internal energy and the specific volume. As written in equation 6, it's possible to identify the term U plus PV, which is equal to the enthalpy. The conclusion is that the enthalpies of the initial and final states are equal. Enthalpies are state properties, and enthalpy differences are independent of the process path. This figure shows a process path that will take advantage of the properties we have available. This virtual process starts with sodium chloride at 25 degrees Celsius, which is the room temperature, and water at 0 degrees. We then take water to 25 degrees Celsius, because the next step is the mixing of sodium chloride with water, and the enthalpy of the solution is available at 25 degrees. After mixing this virtual process, the solution is at 25 degrees Celsius and it needs to be taken to its final temperature, which we do not know, but we will find out by solving the energy balance. The first row of this slide represents the energy balance, the difference in enthalpy between the final and initial states. The subsequent lines break the energy balance into the contributions of the previous slide. There is the change in temperature of the final solution, there is the mixing process, there is the change in the temperature of pure water, all of these terms together comprising the energy balance. In the final line of this slide, these contributions are written in terms of the heat capacities and of the enthalpy of this solution. Replacing the numerical values, we find out that the final temperature is 269.8 Kelvin, which is equivalent to minus 3.3 degrees Celsius. This result clearly shows the effect of the heat of mixing. We started with sodium chloride at 25 degrees Celsius and water at 0 degrees Celsius. But the temperature after mixing is lower than the initial temperature of both pure components. How does this result compare to our experiments? The final experimental temperature was about minus 1 degree Celsius, while the calculated value was minus 3.3 degrees Celsius. Why the mismatch? Many possible reasons. One of them is the uncertainty of this home experiment, and another is the uncertainty of the values adopted for the physical properties in the calculations. But experiments and calculations agree in that the final temperature is below 0 degrees Celsius.
Thank you for watching part 1 of this two-part series on the properties of the water-sodium chloride system. Here we analyze the effect of heat of mixing, and then in the second part of this series we are going to analyze the phase diagram of this mixture. See you in part 2 of this series.